Assalamualaikum and hi everyone, we are Group 1 and in this video we will present an overview of the ARM CORTEX-A78C processor. So before we start, this is our group members. For this presentation, we will cover about 4 content which is introduction, the architecture, performance and conclusion. And let me jump into introduction. For introduction, I will separate it into 3 parts, which is the general overview, its design features and applications. General overview. ARM CORTEX-A78C is a high-performance CPU core from ARM's CORTEX-A family, which is a group of 32-bit and 64-bit RISC ARM processor cores licensed by ARM Holding. These processors are highly efficient and used in a wide range of devices from smartphones to servers. ARM stands for Advanced RISC Machine, a processor architecture designed for energy efficiency and optimal performance. This makes it particularly valuable in portable and battery-operated devices. There are 5 design features, which are: first one is memory system enhancement. The CORTEX-A78C includes up to 8 MB of shared L3 cache, which provides faster access to frequently used data. This is especially important for workloads of professional productivity tools, high-resolution video editing, and AAA gaming. The second one is ARM v8.2A architecture. This is an advanced iteration in the ARM v8A family that brings improvements like better floating point performance, enhanced scalability, and support for new instructions. Third, advanced SIMD instruction. SIMD single instruction multiple data allows the processor to perform the same operation on multiple data points simultaneously. This is critical for tasks like image processing, machine learning, and multimedia application. The fourth one is security features. There are 2 security features, which is PAC, Pointer Authentication Code, and MTE, Memory Tagging Extensions. And the last one is dynamic technologies. Dynamic technology is high performance cores and energy efficient cores are combined. This is upgrade versions from big little architectures and improves multi-core efficiency and allows for flexible scalability across workloads. Next is the various applications of high performance computing. The first one is gaming. This supports AAA gaming by enabling realistic graphics, faster frame rates, and reduced latency. The second one is machine learning and AI inference. It built for handling AI workloads such as neural network processing, and real-time data analysis. The third one is portable devices. The CORTEX-A78C powers smartphones, tablets, and other portable devices that require high performance while conserving battery life. And the fourth one, edge computing. It's designed for edge devices that process data closer to its source. Its ability to manage high-throughput data streams is crucial for IoT devices and edge cloud solutions. And the last one is high-end laptops. This competes with traditional x86 processors in laptops by delivering desktop-level performance in lightweight and portable designs.
Hi, my name is AZIZAN and I'm going to explain about the architecture of CORTEX-A78C. So there are 3 parts of the architecture that we are going to discuss today. The CPU core of CORTEX-A78C, the memory management unit, and the power management of CORTEX-A78C. First, the CPU core of CORTEX-A78C. It is divided into 3 parts: the front end, the middle core, and the execution core. So the front end. The front end fetches a bunch of instructions and sends them to the decoding unit. The first component of the front end is the branch prediction. It predicts the path for the instruction based on the past information acquired. The 2 paths that it may send the instruction to is to the instruction cache, the I cache, or the level 0 macro op cache, the MOP cache. The I cache stores the instruction that has recently been fetched so that the processor does not need to wait to access the main memory to get the instruction, which is much faster. Every instruction that is fetched from the I cache is sent to the middle core to be decoded. The MOP cache has its own decoder that allows instruction to bypass the middle core and be sent straight to the execution unit, which increases the efficiency. Finally, the instruction L1 translation look-aside buffer (TLB) is a component of the memory management unit, the MMU, that helps in address translation. This will be further discussed in the MMU section. Now, the middle core. It is responsible for every decoding process. After the instructions are decoded, the register rename unit will enable the out-of-order execution to resolve the instruction hazard that could override other instruction register. There are 2 techniques for register renaming. First, the explicit renaming. Use a rename table to map an architectural register to a physical register. The other technique is the implicit renaming. The implicit renaming uses a reorder buffer (ROB) that tracks the value of each architectural register. The ROB entry number acts as the physical register identifier. For each register renaming process, it will be undone in the commit stage. The final part of the CPU core is the execution core. It is divided into two units, namely the integer execution unit and the vector execution unit. The integer execution unit handles all the basic logical and arithmetic operation. The vector unit, on the other hand, handles advanced single instruction multiple data (ASIMD) and the floating point operation. Now we will get into the memory management unit, the MMU. There are two parts of this, the level 1 data cache and the main MMU. We will start with the L1 data cache. The main components are the data cache, the D cache that act as primary storage for data that is frequently used so that the processor can access the data faster. The processor will first check the D cache for the data desired before accessing the main memory. If the data exists, it saves the time for the processor without needing to access the main memory. As we can see on the block diagram, there are three addresses generation unit AGU. AGU function to calculate addresses used by the processor to access the main memory. CORTEX-A78C contains an extra load AGU with the two load store AGU. This increases the load bandwidth by 50% to allow faster data fetching. Next, there is the load store queue, the LSQ. It is structure that hold in-flight or operator memory instruction. The memory instruction that is being held is maintained in the program order. The LSQ is designed to absorb large cache bursts and to ensure the memory operation is preserved. The memory management unit, the MMU for short, its main function is to convert virtual addresses to physical addresses. It uses a translation table that includes set of address translation and related memory characteristics that is used in each translation. TLB is a kind of memory cache for storing page table entries (PTE), which speed up the translation process. TLB will check if a page is already in the main memory and retrieve it if it is available. If the page desired isn't found, TLB will be updated with the new PTE. Now we have the component of the MMU, the instruction and the data level 1 TLB and the level 2 TLB. The instruction data level 1 TLB provide a single clock cycle access to the translation, then return the physical addresses to the I cache or D cache respectively. L2 TLB main job is to handle misses from L1 TLBs. L2 TLB also shared by both L1 TLB. Final but not least, we have the power management of the CORTEX-A78C. The three things that will be discussed are the feature power manage and the voltage power domain management. So first, there are two types of power management, the dynamic and the static power management. The dynamic power management first feature is the architectural clock gating. It works by disabling the unused clock in the processor to reduce power consumption. The next feature is the dynamic voltage frequency scaling, VFS. They adjust the voltage and frequency based on the workload, environmental condition, and the required performance. This allows for minimum energy consumption while maintaining the desired performance. Then the low power standby mode that use wait for interrupt WFI and the wait for event WFE mechanism. This mechanism disables most of the core clock while keeping the power of the core active. The core will remain in low power state until a wake up event is occurred. The other power management is the static power management. The feature include dynamic retention. This feature keep the processor in a low power state even if the clock starts momentarily for a short amount of time during the WFI. For the next part, we will start with the voltage domain. Voltage domain is a group design element that share a single voltage supply. For each core, the virtual CPU, vCPU voltage domain, power the CPU core and their processing logic unit. Also, the virtual system VSys voltage domain, power the dynamic shared unit DSU that manage the shared task between the cores. There's also a asynchronous bridge that connect the vCPU and the VSys domain. It also allow communication between domain that operate at different voltage and clock frequency. Finally, the power domain. The power domain is the collection within voltage domain that share a common power strategy. The example figure show that every part that is in the same color shares the same power domain. There are two core power domain in the CORTEX-A78C core. A core power domain DP CPU and the core top level system power domain PDCs. PDCPU contain all the core processing logic except for the cluster clock domain side of the bridge. The PDCs is the interface between CORTEX-A78C and the DSU. It contain all asynchronous bridge for crossing clock domain that manage all core input and output signal via the CPU bridge and the PDCs.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ismail and now I want to talk about performance. The ARM Cortex-A7C is a high-performance CPU core designed for the demanding workloads. Would you understand of its processor to Cortex-A78 is a target application to recurring 8-chain performance, scalability and security. Key features and advantages include: Number 1 is a multi-core scalability, support up to the 8 counter A78C core in a single cluster. Optimize for the homogeneous multiplication and increase consistent performance across core. Ideal for the multi-threaded workload, providing significant performance for tasks like gaming, CAD, and organized rendering engines. Number 2 is a LT cache explanation. Explanation is a AMD LT cache. Beneficial of application with a longer data asset, improve performance in the high throughput and high thread count experience as a gaming and professional software. Number three is a single core performance. Besides precision and execution efficiency. Profit profits improve single thread performance compared to the Cortex-A77. Number four is a process not efficient. Manufacturing is a use 7M or the 5M to process technology enabling highest clock speed, better energy efficient. Number five is a gaming optimization paired with the Mali G78 GPU. Experiencing graphic performance, improved battery life during intensive gaming season, designed for the all-day gaming and impossible experience even for the next generation AA games. Using Core High and digital experience, such a gaming, professional application and workloads requiring consistent GPU power. A scalable design tolerate for the workloads like organic rendering, complex simulation, and continuous productivities. Conclusion: Cortex-A7C is usually a variant of the high-performance and low-power competition, making it ideal for the portable and battery-operated device. In efficient performance per watt, enabling excited using with the minimal power and heat generation preventing overheating issue. Overseas executive features protect against cyber threat, ensuring user data safety. The Cortex-A7C is well suited for multitasking, especially with AFIF and conflict workloads. Overall, it's a versatile and label processor for the various applications, offering using and conform efficient and security.